Hi guys, your friend Gopika is here, and in this video we will discuss the practice set 3.2, wherein we will be using the concept of touching circles, the theorem of touching circles, and the distance between their centers concept. Okay, so without wasting time, let's get started. So this is the first question in your practice set. Two circles having radii 3.5 centimeters and 4.8 centimeters touch each other internally. Okay, find the distance between their centers. So always whenever you get such a question, it would be preferable if you draw a diagram and then find the answer, because once you draw the diagram, the concept is really simpler. So internally means this is how these circles will look like. So make a rough diagram. Now here X is the center of the smaller circle and Z is the center of the larger circle. Y is the point of contact. Okay. Now the two circles having radii 3.5 centimeters. That means the smaller circle radius is 3.5 centimeters. Larger circle the radius is 4.8 centimeters. They're touching each other internally. We need to find the distance between their centers. That means we need to find xz. Okay. Distance between x, z. So the circles touch internally, therefore the distance between their centers is difference between their radii. Why? Because if you observe this zy is radius of the larger circle, xy is the radius of the smaller circle. From zy, if you subtract xy, then you will get xz, which is the distance between their centers. That means xz is equal to yz minus yx, and that would be 4.8 minus 3.5, and that would be 1.3 centimeters. That means the distance between the centers of the circles is 1.3 centimeters. So whenever you have two circles touching internally, the distance between the centers is difference between their radii. Okay, now let's see the next problem. Here the circles are touching externally. So if you see the figure like this, the circles are touching. Okay, one circle has radius 5.5 centimeters, other one has radius 4.2 centimeters. We need to find the distance between the centers. Now here distance between the centers is xz, and it will be equal to xy plus yz. That means radius 1 plus radius 2. So here the radii is getting added. So when the circles touch externally, the radii will get added. When the circles touch internally, the radii will get subtracted whenever you want to find the distance between the centers. So in this case, since the circles touch externally, the distance between the centers is sum of the radii. That means xz is xy plus yz, and xy is 5.5 plus yz is 4.2. So xz is 9.7 centimeters. So that is the distance between their centers. Okay. So let's move on to the next problem. This is the third question. Here you need to do small construction, nothing else. If radii of two circles are 4 centimeters and 2.8 centimeters, draw a figure of these circles touching each other, case 1 externally, case 2 internally. So both cases you have to draw. For that, whenever you want to show that externally two circles are touching, to get a perfect diagram, what you do, first you add this radii, that is 4 plus 2.8, that will be 6.8. Draw a straight line, horizontal line of 6.8 centimeters. Okay. Now on the first end, you keep the compass, the pointer of the compass, and take radius 4 centimeters and draw a circle. And the next end point of the segment, keep the pointer of the compass, take 2.8 as radius and draw the circle. So if you do this perfectly, you will see that the two circles are touching at one point y. Okay, so draw a straight line segment of 6.8 centimeters. From one end, draw a circle of radius 4 centimeters, and keeping the pointer on the other end, draw a circle with radius 2.8 centimeters, and hence you get a perfect diagram. Then draw the common tangent also. Okay, this showing common tangent is important in the concept of touching circles. Okay, next, in the second case, whenever you want to draw internally, what you do, again So here, now here in external case, the radii get added. Okay, now here you don't need to do that. Draw a line segment of 4 centimeters. Okay, now keep the pointer and draw a circle. Okay, at Z. Now Z is the center of the larger circle. So keep the pointer there, keep it at the end of the segment and then draw a circle. Next, keep the pointer at at X. That means how you will choose X then. Take the scale and from this point Y measure 2.8 and make a marking over there. Keep the pointer of the compass over there and then keep the pencil here and draw one more circle. So here also two internal touching circles you can draw easily. Okay, then show the common tangent also. That's it. So common tangent, point of contact and two centers. This much you have to mark. That's it with the third question. Now let's say the fourth question. Here in the figure 3.27, that is towards your right, if you see in this particular diagram, the circles, there are two circles, one with center P and another with center Q. Okay, they touch each other and their common point of contact is R. Now a line passing through R meets the circles at point A and B respectively. That they are talking about this line. Okay, this line AB is passing through R. Now we need to prove that this particular segment AP is parallel to segment BQ. Okay, so that is what we need to prove. So consider these two triangles. If you see this triangle PAR and this triangle RQB. Okay, so there, now in triangle PAR, this PA and PR are radii of the smaller circle. That means this particular triangle is an isosceles triangle since two sides are congruent. That is, side PA is congruent to side PR since they are radii of the same circle. That means by isosceles triangle theorem, this particular angle PAR is congruent to angle PRA. Okay, since PA is congruent to PR, the angles opposite to it are also congruent. That means angle PAR is congruent to angle PRA. Similarly, same thing you can apply to triangle BQR or RQB. Since QR and QB are radii of the same circle, they are congruent sides of the triangle. That means this triangle is also isosceles triangle and hence angle QRB is equal to angle QBR by isosceles triangle theorem. So mark these 2 points as point 1 and point 2. Okay. Now here this angles PRA and QRB, they are vertically opposite angles. Okay, that means they are on the opposite sides of two intersecting lines. If you see, those are vertically opposite angles. That means they are congruent again. So these two angles are congruent. That you mark that point as 3. So if you compare this point 1, point 2 and point 3, you will observe that this particular angle PAR is congruent to angle QBR. Okay, for very simple reason, A is equal to R, here B is equal to R and here R, both the sides is equal. That means A is equal to angle B. So angle PAR is equal to angle QBR. Now those are alternate angles. So by alternate angles test, we can say that this particular segment BA is parallel to segment BQ and hence proved. So we consider these two triangles, apply isosceles triangle theorem, and then we consider the vertically opposite angles over here. They are congruent and hence we get that the alternate angles PAR is congruent to angle QBR. That means the line segments PA is parallel to BQ and hence proved. Now let's see the next question. Okay, so the same question has 3 parts. One part we discussed. The second part is triangle APR is similar to triangle RQB. That is, triangle APR is similar to triangle RQB. That is what we need to prove. Now once we prove that PA and QB are parallel segments, we can say that angles PAR is congruent to angle QBR and angle APR is congruent to angle RQB. Any two angles, any two set of angles you write, two set of alternate angles you write, by AA test the triangles are similar. Okay, or you can also use those angles which we discussed in the first part. Two set angles we already discussed in the first part regarding these two triangles. One was the vertically opposite angles and other was these two. That also you can use to say by AA test the two triangles are similar. Next, the third part is RQB. We need to find the measure of angle RQB if angle PAR is 35 degrees. That means this particular angle PAR is 35 degrees. You need to find RQB. Now, if PAR is 35, then RBQ is also 35. Since angle RBQ is equal to 35, that means angle BRQ is also 35 degrees. Now, these two angles are congruent by isosceles triangle theorem, and PAR is equal to BRQ, and hence PAR is equal to RBQ, and hence this is also 35. Now, RBQ is 35, that means BRQ is also 35. So, we got these two angles. Now, in this particular triangle, we know angle R, we know angle B. We can find angle Q by applying the angle addition property. Since sum of angles of triangle is 180 degree, apply that property over here. So, 35 degrees plus 35 degrees plus angle RQB is 180 degrees. Now, 35 plus 35 is 70 degrees. That means angle RQB is equal to 180 degree minus 70 degrees, and that is 110 degrees. So, angle RQB is 110 degrees. Okay. So, let's move on to the next problem. Here, in the figure 3.28, in this particular figure, the circles with centers A, the first circle is with center A, and second circle is with center B, touch each other at point E. E is the point of contact. Now, line L is a common tangent which touches the circles at C and D respectively. So, this particular tangent is common to both the circles. Now, find the length of segment CD if the radii of the circles are 4 centimeters and 6 centimeters. So, we need to find this length CD, and radius of the first circle is 4 centimeters and radius of the second circle is 6 centimeters. Okay. So, here we make few constructions. First thing that we will do is first join this AC, which is radii of the circle. Then joined BD, which is again radii of the circle, radius of the second circle. Next, this joined this AB. So joining the center. So E is lying on this particular line. And then if you see, you will get a quadrilateral ABCD. Okay. But now this quadrilateral is not a rectangle or anything. So again, we cannot use anything over there. So we make one more construction by joining AF such that it is perpendicular to BD. Okay, this AF is perpendicular to BD. So construct AF perpendicular to BD. Rest we were just joining the segments. Now C, A, D, B, A, B, everything we joined. A new construction that we made is finding a point AF such that it is perpendicular to BD. Okay. Now angle AFD is 90 degrees. Okay. Also, this angle ACD and angle BDC are 90 degrees since by tangent theorem radius is perpendicular to the tangent. So, at the base this angle C and angle D is also 90 degrees. So, those two angles are also 90 degrees. So, we have a quadrilateral with three angles 90 degree. That means the fourth angle is also 90 degree. Hence, this quadrilateral is a rectangle. Now, we cannot say it is a square since we don't know if the sides are congruent, but at least it's a rectangle. Okay. Now it's a rectangle, that means the opposite sides are congruent. So this FD is same as AC, and AC is radius of the smaller circle, which is 4 centimeters. So AC is 4 centimeters, so FD is also 4 centimeters. Next, AF is equal to CD. So just mark it as star. Now we don't know anything regarding it. Now if AF is equal to CD, and if you find length of AF, then it is same as length of CD, right? And length of CD we need to find. So first we will find length of AF. For that, what we will do, we will consider this small triangle BFA, this particular triangle BFA, where this angle F is 90 degrees, and hence we can apply Pythagoras theorem over there. Now before applying to apply the Pythagoras theorem, note that this AB, we need the length of this AB, and then we need the length of BF, hence we can find AF. Now AB's length will be same as AE plus EB, right? AE is radius, so 4 centimeters. BE is also radius, that is 6 centimeters. 4 plus 6 is 10, so AB is 10 centimeters. Next, so that is one thing wrote over here. Next, here BD we know that it is 6 centimeters, correct? FD we found that it is 4 centimeters since it is equal to AC. Now BD is 6, FD is 4, that means BF is 2. Since BF will be BD minus FD, that is 6 minus 4, hence BF will be 2 centimeters. So AB is 10 centimeters, BF is 2 centimeters. Now in this particular triangle BFA, if you apply Pythagoras theorem, then you can find the length of the side AF. So angle BFA is 90 degrees, hence AB is the hypotenuse. So AB square is same as AF square plus FD square, that is by Pythagoras theorem. Now AB is 10, so 10 square is equal to AF square plus FD is 2, so 2 square. Therefore, AF square is 100 minus 4. 10 square is 100 and 2 square is 4. 100 minus 4 is 96. That means AF is square root of 96, and 96 same as 16 into 6. 16 is 4 square. So 4 will come outside and that would be 4 root 6. Okay. So this AF is of length 4 root 6 centimeters. Now since CD is equal to AF, that means CD is also 4 root 6 centimeters from star, because in star we wrote the equality. So CD is 4 root 6 centimeters. So that's all with practice set 3.2. If you like the video, please share it with your friends and please subscribe the channel. You can also follow us on Instagram and post your queries. We will respond as soon as possible.